So in this video, I'm going to be covering some of the material from chapter 31, but before we get started on that, I want to remind you about what we learned in chapter 30. So the idea there was that EMF and current were induced by changing the flux through the circuit with respect to time. If this was our circuit, and we started off by having this magnetic field going into the page like this, well, nothing happens, right? Like we just have a magnetic field, there's no induced current. The current only gets induced whenever we start changing things. So here, let's say I start adding field lines that are going into the page. Well, we know from Faraday's law that this is going to give us a current, and we know from Lenz's law that that current is going to be pointing in such a direction that it induces a magnetic field that opposes this change. So the change is magnetic field going in the x direction, and then more magnetic field going in the x direction. So it's an increase in that x direction. By x, I just mean into the page. So then the induced magnetic field is going to be coming out of the page like this. To get that type of magnetic field, by the second right-hand rule, my current has to be flowing counterclockwise. So now we're going to look at self-inductance, which is when this whole thing occurs within a single circuit like this. So if we zoom in here, we have a switch, and we're going to pretend that the switch is open. When the switch is open, there is no current flowing through the circuit. If we were to then close the switch, all of a sudden there is current flowing. So this is a change, right? We start off by having no magnetic field lines, and then we have magnetic field lines because we know that moving charges produce these magnetic field lines that are going in this direction here. And so then we know by Lenz's law that, well, we have this change in flux, so my current is going to be such to oppose this change in flux. That's going to mean that my induced current is going to be pointing in this direction here. So my normal current's going like this, and my induced current's going like this. Essentially what this looks like is when I close my switch, I don't immediately have my current jumping from 0 to Imax. There's this slowdown caused by this backwards EMF that then produces this current that's opposing it. Eventually, yeah, my current is going to reach Imax, like we're going to see in a bit, but it takes a certain amount of time. Mathematically, we express EL, which is the kind of like back EMF due to that self-inductance, is equal to negative L, where L is just a proportionality constant that's called the inductance, times di over dt, where we know that this is what is giving us these magnetic field lines and is the reason why we have this inductance happening in the first place. But we also know that this is Faraday's law, so we can compare the two. And by comparing them, we see that L, the inductance, is equal to N phi B over I. The SI units of inductance are the Henry, and 1 Henry is 1 volt second per amp. So the inductance is a measure of the opposition to a change in current. It depends on the coil's geometry. This is kind of like when we talked about capacitance and capacitors, where the capacitance was what is the capacity of the capacitor to hold that charge. Here, it's how good is the circuit at producing this like backwards current that slows down the process. If we were to look at the inductance of a solenoid, for instance, we have here the flux is equal to B times A in a very simple scenario, and we know that B is just equal to mu naught N times I, where I is in lowercase because it's changing with respect to time. And so we can write it out like this, and then we take this answer here, plug it back into our inductance, and we get L is equal to mu naught N squared A over L. So it really depends on what is the area. Here for a solenoid, it depends on how many turns you have, inversely on how long is it. So it's really this geometry type of proportionality constant. So what we see is that solenoids are a type of circuit element that are relatively easy to control. Like you can control how many loops you have, how big it is. So we're going to use them as our inductor component. But really any circuit element that has a large inductance is an inductor. So if we look at an RL circuit, it looks like this, where we have a resistor and we have an inductor. Let's now look at what happens when we turn it on. So S2, this switch is set to A, like this, and S1 is open. At t is equal to 0, we close S1. So this allows the current to flow through the resistor and through the inductor. Now, if we were to use Kirchhoff's loop rule, we see that E, this is the EMF from the battery, minus I times R, which is for the resistor, minus L di over dt, which comes from the inductor that we saw up here, right, is equal to 0. So Kirchhoff's second rule. We want to figure out what is the current at any given moment in time. So to do this, we need to solve for I in this equation, and so we're going to use a couple substitutions. The first, we're going to call x e over r minus I, and then dx is equal to negative di, because here, the only component that's really changing is going to be your current. So now let's take these values and substitute them back into our main equation. We do that, and we get this here. So x plus L over r dx over dt is equal to 0. We've done similar things before, where we're going to take everything that has an x onto one side, and everything else goes to the other side. X starts off at some value, and it goes to some value. Time starts at 0, goes to t. We take the integral, and we get this, and on this side, we get this. So now, if we were to do the exponents, we do e to the power of ln, that disappears, so we just get x divided by x naught, and then e to the power of negative rt over L, that sticks here, and we get this. So this is our answer. But now we don't want the answer in terms of x, we want the answer in terms of I. So what we're going to say is, well, what is x naught? X naught is the value of x at time is equal to 0. At t is equal to 0, the current is 0. So then if we look here, well, if I is equal to 0, at t is equal to 0, x naught is just equal to e divided by r. So that's what we have here. So all I did was replace x naught with e over r, and then e to the negative rt over L. Now, x is also equal to e over r minus I. So I put that here. All we do now is take this part of the equation, isolate for I, and we get this, where the current at any given moment in time is equal to e divided by r times 1 minus e to the negative rt over L. Now, if we were to plot this, we'd have something like this, where here on the x-axis we have t, the time, and on the y-axis we have the current. So we see that the current starts off at 0, at time is equal to 0, and then it increases all the way up until it gets to its maximum value after a certain amount of time. We define this variable similar to what we've done previously, where t, or tau, is the time constant, and it's equal to L divided by r. The time constant is just the time interval required for the current to reach 1 minus e to the negative 1 of its final value. So just a way to talk about like how fast is it increasing, how slow is it increasing. If we also wanted to talk about the derivative of I with respect to time, we take the derivative of this and we get this. We can also plot it. But I think understanding this first one of how I is changing with respect to time is a little bit more useful. So we can now look at the opposite case, where here S2 has been set at A for a long enough time to allow the current to max out and reach I is equal to E over R. If S2, so here this switch, is then thrown from A to B, well, the battery's gone now and we just have this circuit here. So the circuit is just R and it's just L. We're going to again use Kirchhoff's loop rule, where we have I times R plus L di over dt is equal to 0. Put them on either sides, you get this. IR is equal to negative L di over dt. We're going to do the same thing, put everything that has a time onto one side, everything that has a current onto the other side. This time, or bounds, we're going to again just say time starts at 0 and goes to t. And here for the current, it starts off at some value I naught. Here we know that it's at its max value, E over R, but it could be anything. And it stops at current equal to I after some time t. We're going to again solve these integrals and we get this. So it's RT over L and then is equal to ln I over I naught. I'm just going to isolate for I and I get this. I naught is equal to E over R and we get this set of equations here. It's a very, very similar thing where here we start off at some value and then we have this exponential decrease all the way until we get no current at all. But it does not happen immediately, right? Like it's a slow relatively slow, depending on how you think of it, process because of that solenoid. So it tapers off like this. The last thing I want to talk about in this video is energy in a magnetic field, just because we're going to be using this equation in the next video when we talk about LC circuits. So the energy from the battery goes to two places. It goes to the resistor, but it also goes to the magnetic field of the inductor. So it goes here and it goes here. If we were to take our Kirchhoff's loop rule, the one that includes the battery, and we were to multiply it by I, we get this. So I times E, which is just the battery voltage, is equal to I squared R. This is for the resistor. And then plus Li di over dt for the inductor. This here is the rate at which the energy is stored in the inductor that can be represented as dUB over dt, where this is the magnetic potential energy. So this is our equation just from here. We're going to solve for UB by just taking the integral of both sides, and we're going from 0 to I. So it's like, what is the energy stored in the inductor? Well, it depends how much current did we start with, so 0. How much did we end with? I. Integral of Li di. And then L is just a constant. Integral of I di, that's just going to be I squared divided by 2. So that means U of B, the amount of energy stored in the inductor, is equal to 1/2 Li squared. And that is it for this video.